This video supplies our ICRA 24 submission, bridging the sim-to-real gap with dynamic compliance tuning for industrial insertion. Industrial insertion is challenging to automate due to the tight clearance. The video below shows an example of this assembly task, which is difficult even for human operators. This tight clearance results in a complex contact dynamics, and sim-to-real gap exists for transferring the robot skills from simulation to the real world. In this paper, we focus on the sim-to-real transfer problem for industrial insertion. Our intuition is that by adjusting the robot's compliance gains during task execution, we can adaptively modulate the contact forces in the real world to match the desired contact force, and thus generate similar trajectories as the simulation. Our proposed approach consists of two phases. First, we collect an insertion dataset in simulation using a reinforcement learning agent to offline train two networks, a gain tuner which predicts the suitable compliance gains to achieve the desired force, and a force planner which plans with the robot motion and next contact force to achieve a desired return. During the real-world insertion task, we first use the force planner to generate robot motion and desired force. Then, the gain tuner actively updates the admittance control gain for the robot given the force plan and previous trajectory to modulate the real-world contact force. We validated our proposed method in three sets of real-world insertion tasks. The first set includes 3D printed peg holes with tight clearance, which require high accuracy of alignment. The tightest task is very challenging as the pegs stick to the hole after insertion and failed out of the gripper. The second set contains electronic connectors with complex shapes. In those tasks, we tested the generalization ability of our method. The third set has two skateboard truck assembly tasks, which require the robot to apply suitable amount of force to deform the hole. For all the tasks, our method achieves promising success rates with direct sim-to-real transfer and outperforms all the baselines. We also plotted the contact force and corresponding gain during insertion. As shown in the video, our proposed method dynamically adjusts the gains to match the planned contact force and finish the insertion task efficiently. In comparison, the two baseline methods lack the capability to modulate the contact force. In return, they exhibit noisy and unstable contact force, leading to lower success rates. Finally, we show some failure cases. Since the keeping task involves metal parts contact, our proposed method could generate a large contact force and cause a protective stop. We found out that fine-tuning the force planner with a small amount of real-world data can help to achieve better performance. As a result, the success rate increased from 70% to 100% after the fine-tuning. That concludes our work. Thank you for watching.